Hello, statistics students. Up until now, we've been working in the branch of statistics known as descriptive statistics, where we gather, organize, and display data. Starting in this chapter, we're going to be working in the branch of inferential statistics, where we make an inference or we draw a conclusion about a population based on a sample. So for an example, I want to know what mu is. I want to know what the population mean is. Well, if I take a sample and I get X bar, that X bar is what we call a point estimate of mu. It's an estimate. It may be good or it may be bad, but it's 1 point. I think we'd all feel a little bit better rather than saying, okay, that X bar is close to mu. Let's give it a margin of error. Let's say, all right, we think mu is X bar plus or minus some amount. That should seem reasonable to us. And we're going to let C be our level of confidence. Check page 299 of our current textbook for what C, a level of confidence, is. We'll go over it more in class. So what we have here is X bar. It's going to be in the middle of what's known as a confidence interval. You go X bar minus E and X bar plus E. So X bar is right in the middle. Well, as an example, and as a very common example, let's let C, our confidence level, be 95%. C is the fraction of times that your confidence interval that you would create actually contains mu. That is very important because there are two ways people describe what C is. And the first way is not correct. We don't say there's a 95% chance that mu is in the confidence interval. We say there's a 95% chance that the confidence interval contains mu. And here's the reasoning behind that. We never, ever make an inference, or we never, ever make a probability statement about mu, about the parameter. We make a probability statement about our process. There's our sampling process that gave us that sample. There's a 95% chance that that sample contains mu. It's subtle, but very important. There's another field of statistics where you actually do make probability statements about the parameters themselves. That's beyond the scope of this course. So let's talk about what a confidence interval is. Let's say that we have a population, we don't know mu, but somehow we magically know sigma. Even though to calculate sigma, if you recall, you needed mu because it was your data point minus mu, quantity squared, add them up, et cetera, to get the variance, divide by either n or n minus 1. Then we took the square root to get the standard deviation. So we needed mu. But we always assume we know sigma to start because that makes life easy for us. So we take a simple random sample of 840 and I get an, let's see, we need to shrink this a smidge, I think. There we go. So I get a sample of 200, sample average of 272, and we'll come up with where this 4.2 came from in a minute. And then I did another sample of 840 and I came up with this confidence interval. And I did another sample of 840 and I came up with this confidence interval. When we say that we have a 95% confidence interval, that means that 95% of the intervals will capture mu. Not that there's a 95% chance that mu is in the interval. Correctly, we state there's a 95% chance that the interval contains mu. Now, if we go to, let's see, I'm not even sure if that changed, so I'll just screen share again just to make sure the picture changed. So if here's our normally distributed data, and here's mu, if I take a sample, I might get this X bar, plus or minus, and it'll be 2 standard deviations, because if you remember, 2 standard deviations is approximately 95% of our data. So plus or minus 2 standard deviations, you see that this confidence interval contains mu. Now I can get another sample will be this X bar, plus or minus, our margin of error. It contains mu. I did get a fluky sample up here that doesn't, but most of the samples you can see are going to be hovered in here. That sample means are going to be hovered in here near mu, and certainly the confidence interval contains mu. So in the long run, if you do your sampling based on a simple random sample, etc., 95% of all the samples will give you an interval that contains the population mean mu. If you can understand this concept, you are well on your way to success in this section. So let's go back and make sure that we understand this point. You don't make a probability statement about the parameter, you make it about your process, your procedure, your sampling. Now here's the bottom of page 299 in our textbook, current textbook. I have no idea what year you're watching this video. So here is a 90% confidence interval. So if C equals 90, we're talking 90, the middle 90%. So 1 minus C is the area in the tails. So each tail is 1/2 of 1 minus C. So what Z-score marks off the bottom 5%? Well, that would be negative 1.645, and the Z-score that marks off the top 5% would be positive 1.645. You should do this same drill with a C equals 95%. See if you can come up with these numbers, and what you should get is a Z-score of plus or minus 1.96 for 95%. Give it a try on your own. Make sure that you can do that. So just as a reminder from what we learned at the end of last chapter is about a sampling distribution and the central limit theorem. Here's a normally distributed population with a mean of mu and a standard dev of sigma. The sampling distribution of those X bars will have a mean of the same mu, but a standard dev that's this sigma up here divided by the square root of n being your sample size. So sigma over root n is your standard dev, and Z critical, your Z-score is going to tell you, is going to be based on what your level of confidence is. So a Z-score of 1.96 is a confidence of 95%. So if we wanted a 95% confidence interval, we wanted that middle 95% of data, we'd say, well, that's 1.96 standard devs. So here's your standard dev, or at least standard error, but you get what I mean. So here's the standard dev of your distribution. Here's how many standard devs you have to go in order to get that level of confidence. So your confidence interval was X bar plus or minus E. Well, now we know what E is. So mu, your confidence interval is between X bar minus your margin of error and X bar plus your margin of error. And again, your margin of error is this is your standard dev. This is how many standard devs you have to go in order to get this level of confidence. Now take a look at page 301 of our current text. Page 301 of our current text tells us, here's our formula for a confidence interval. Here's how you create a confidence interval. It's all the steps that I've just given you. So what we're trying to do now is we're trying to estimate mu. What is mu? Based on our sample, mu is going to be between, some low number x bar minus your margin error and some high number x bar plus your margin of error. That's why we write it like this: x bar plus your margin of error, x bar minus your margin of error. And that z critical, we call it, is based on your confidence level C. How many standard deviations do you want? What if you have a fixed margin of error? So in our current textbook, page 305, number 21, in case you don't have our current textbook, let's see what it says. Oh, that's easy. It says construct the confidence interval for the population mean mu. And then it says C is 90%. Okay, all the data is there that I have. So we're just going to construct a confidence interval. So we want a 90% confidence interval. That means that it's not that we're 90% confident that our confidence interval, that mu is in our confidence interval. We're going to be 90% confident that our confidence interval contains mu. So we took a sample, and remember, sample could be a fluky one, could be all the high numbers or all the low numbers. But we got a sample of 12.3 inches, and somehow we know the population sigma is 1.5, and we have a sample size of 50. So C of 90% gives us a Z critical value of 1.645. If you look in your book, our current textbook on page A16, 17, at the bottom of page A16 is a Z critical value for some common levels of confidence. All right, and you see here that we came up with 12.3 inches plus or minus a little over 1/3 of an inch. What if we're in a manufacturing environment and our margin of error can allow no more than 1/4 of an inch? You can't be more than 1/4 of an inch short or long, otherwise the part doesn't work. What sample size would give us a margin of error of less than 1/4 of an inch? Well, here's your formula for margin of error, and I'm going to solve for n. So I'm going to multiply both sides by root n, divide both sides by big E, and then I'm going to take this, or I'm going to square both sides. So n is now the minimum necessary sample size to get a specific margin of error. So if I wanted still a 90% confidence interval, I have 1.645. Sigma, we know that 1/4 of an inch was our margin of error. We square it, get 97.4. Now you might say, okay, we'll round down to 97. 97.4 is the minimum sample size that will give us a margin of error of 1/4 of an inch. So 97 isn't big enough. We have to round up to 98. This is one of those times where I say statistics is a thinking person's course. You can't just plug and chug numbers. You have to think about what the numbers mean. And there are times in statistics where we round normally, like you're doing a z-score. There are times when we always round down. Here's a time where we always round up if n doesn't come out exact. That n is the minimum sample size necessary to give us the margin of error we want. So we would have to take a sample size of 98. What I would encourage you to do to check my work, go back here and calculate your margin of error with a sample size of 97. You'll see that it will not give you a margin of error of less than 1/4 of an inch or equal to. Then go back and redo the margin of error with a sample size of 98, and you'll see that it will satisfy the requirement of a 1/4 inch margin of error. So starting in this chapter, it's a really exciting field of statistics, inferential statistics. Right now, we're just going to estimate mu, and we're going to do that a few different ways. We're going to estimate mu assuming we know sigma, which we've done in this section. We'll estimate mu in a more realistic setting where we don't know sigma, where we'll have to just use our sample standard dev S. And then we'll also do a confidence interval for a proportion. You know, if a sample, a poll says that candidate A has, 49%, approval rating, or, 49% of the likely voters will vote for candidate A, what is that telling us? So it's a really exciting section of statistics, and hope you enjoy it as much as I do. Have a great day.